At 04:12 a.m. UTC, February 18, 2026, a fresh data packet arrived simultaneously at mission terminals in Maryland, Darmstadt, and Santiago. The image had been captured just 38 minutes earlier by the near-infrared camera aboard the James Webb Space Telescope. Within seconds, automated anomaly flags triggered across 3 independent monitoring systems. What the image showed was not debris, not a fading coma, not a cold, inert remnant drifting into darkness. 3I Atlas was still active. Moments later, a second confirmation came from the Atacama Large Millimeter Array in northern Chile. Thermal signatures had increased by 17% in less than 6 hours. That was not decay. That was energy. Today, the impossible just happened. If you want real-time updates as this story unfolds, subscribe now, because what we are about to discuss changes everything we thought we knew about interstellar objects. For months, agencies assumed 3I Atlas had stabilized after its violent perihelion passage. Following fragmentation events and asymmetric outgassing, models predicted gradual dormancy. But the February 2026 update shattered those expectations. The first alerts were reviewed at mission control centers linked to NASA and European Space Agency. Spectral data was cross-checked against archives from the Hubble Space Telescope and deep field comparisons run through observatories coordinated by Harvard University and California Institute of Technology. 3 continents, 5 independent instruments, identical conclusion. 3I Atlas was not cooling. The new image revealed a faint but sharply defined jet extending nearly 2,400 kilometers from the nucleus, far too coherent for residual sublimation alone. Thermal signatures showed localized hotspots measuring 312 Kelvin, significantly above expected equilibrium temperatures at its current heliocentric distance of 3.8 AU. 48 hours before this discovery, nothing unusual had been reported. Photometric curves were stable. Spin rate appeared consistent at 7.2 hours per rotation. Surface albedo variations were within predicted limits. Then, 36 hours before the alert, subtle changes emerged. An observatory in South Africa recorded a 0.04 magnitude fluctuation, barely above noise threshold. 11 hours later, radio telescopes in Spain detected intermittent broadband emissions between 1.42 and 1.67 gigahertz. Initially dismissed as interference, the signals reappeared with consistent 11-minute intervals. Precision, repetition. 22 hours before the February 18th image, gravitational modeling teams noticed a deviation in trajectory. The acceleration measured 0.00043 meters per second squared, beyond what solar radiation pressure could explain. That number seems microscopic, but in orbital mechanics, such discrepancies rewrite equations. I remember staring at the trajectory overlay as the predictive path drifted millimeters off its expected course, millimeters on a screen representing millions of kilometers in space. No natural outgassing model could account for the vector symmetry. Then came the image. High-resolution near-infrared frames displayed structural changes along the primary fragment's leading edge. The surface, previously irregular and chaotic, now showed a band of uniform reflectivity, almost metallic in spectral response. Not ice, not silicate, something denser. Temperature gradients were equally unsettling. Instead of dissipating outward, heat appeared concentrated along a narrow equatorial ridge, as though energy were being generated internally rather than absorbed externally. 11 hours after the initial image release, a second anomaly struck. The European Space Network recorded polarized light fluctuations at 620 nanometers, precisely synchronized with the earlier radio pulses. This was no longer random. Dr. Elena Vorin at Caltech ran rapid computational simulations. Her team input every known variable: rotational stress, tidal forces, residual cryovolcanism. None reproduced the measured energy distribution. Even exotic scenarios, radioactive decay pockets, trapped volatiles, failed to generate the symmetrical jet structure seen in the image. Two hypotheses began to form. The mainstream explanation argued that 3I Atlas contained unusually volatile compounds, perhaps hydrogen clathrates, that could trigger episodic heating as subsurface cavities collapsed. According to this model, delayed internal fracturing exposed fresh material, producing sudden thermal spikes and coherent jets. It was rare, but not impossible. The alternative hypothesis was more difficult to articulate in official briefings. What if the activity was not passive release, but regulated emission? At 1807 UTC, February 18th, the Atacama Array detected a refined signal structure embedded within the broadband emissions. Fourier analysis revealed spacing patterns consistent with prime number intervals 2, 3, 5, 7, 11. A coincidence? Possibly. But when the sequence repeated exactly 31 minutes later, confidence in randomness began to erode. No known natural astrophysical process generates prime number radio spacing with such consistency. 36 hours after the first image, another shock wave rippled through the scientific community. The equatorial ridge seen in infrared shifted position relative to the rotation axis, not dramatically, but measurably, as if the object were adjusting orientation. Silent motion. Gravitational perturbation models from Harvard indicated microthrust behavior, controlled bursts altering spin by fractions of a degree. The net effect over 24 hours, a 0.08-degree axial correction. Insignificant for a comet, precise for a maneuver. Internal communications between NASA and ESA shifted tone. Language like anomalous was replaced by persistent. Data review sessions extended through the night. Encryption protocols tightened. Public statements became carefully neutral. Then came the second wave. On February 20th at 02:14 UTC, satellite arrays monitoring Earth's magnetosphere registered a faint nanotesla disturbance, barely perceptible. Simultaneously, 3I Atlas emitted a narrowband burst at 8.4 GHz, lasting 2.3 seconds. The timing correlation was within 0.7 seconds of light travel expectations. The object was 3.9 AU from Earth. The delay matched perfectly. This was no longer random. It was responding. Dr. Markus Ilyanov from a European astrophysics consortium argued passionately for restraint. Correlation does not imply causation, he stated in a closed briefing. We are projecting intent onto noise. Others were less certain. Spectroscopy now revealed trace ionized metals in the jet plume, iron and nickel signatures at intensities inconsistent with primitive cometary composition. Either 3I Atlas formed in a radically different stellar environment, or something had altered its structure. Meanwhile, subtle effects on Earth accumulated. 2 communication satellites reported transient signal dropouts. Airline pilots over the South Atlantic noted minor compass deviations. Migratory tracking studies suggested altered avian navigation patterns during the strongest emission windows. Individually, trivial. Collectively, unsettling. 48 hours after the first anomaly, the James Webb Telescope captured another image. Clearer, closer, undeniable. The equatorial ridge had expanded. Linear features extended outward in geometric repetition, spaced at approximately 120 meters. Nature favors chaos. This was alignment.
Thermal output increased again, now 336 Kelvin at localized hotspots. Energy production exceeded solar input by 4%, impossible without internal generation. Simulations grew increasingly desperate. Teams modeled tidal induction, dark matter interaction, even microscopic black hole capture scenarios. Each failed to reproduce the combined acceleration, emission patterns, and structural symmetry. Within control rooms, the atmosphere changed. Conversations grew quieter. Screens glowed against sleepless faces. Governments requested briefings. Intelligence agencies monitored open scientific channels. Publicly, statements emphasized uncertainty. Privately, contingency frameworks were drafted. And yet, amid the tension, a deeper question emerged. What if 3I Atlas is not escalating, but awakening? I pause here, not in fear, but in recognition of scale. Humanity has watched the cosmos for centuries, searching for anomalies that challenge our isolation. We expected silence, or perhaps chaos. We did not expect precision. Maybe we're not witnessing the end, but an invitation. An object from interstellar space surviving perihelion, fragmenting, reassembling behaviorally, emitting structured signals, adjusting orientation with measurable thrust. This narrative stretches the boundary between astrophysics and possibility. But caution remains essential. Extraordinary claims demand extraordinary evidence. The data is compelling, not conclusive. Prime number pulses may conceal natural harmonics. Metallic signatures could originate from exotic stellar nurseries. Microaccelerations might result from anisotropic mass loss still poorly understood. Science advances by resisting temptation. Yet, as of this February 2026 update, one fact is undeniable. 3I Atlas is still active. It has not faded. It has not cooled. It has not drifted quietly into obscurity. Instead, it has intensified. The next observation window opens in 72 hours. Instruments across Earth and orbit stand ready. If emissions repeat, if structural symmetry sharpens, if acceleration increases, then models will fracture under their own assumptions. And if the pulses return, spaced again in mathematical sequence, aimed precisely across interplanetary space, we will face a question no civilization has ever answered. Is this object merely a relic of distant star formation? Or is it something constructed, ancient and patient, crossing the void until it encountered us? For now, we watch, we measure, we wait. Because what happens when it wakes up again?